So in this lecture, we are concluding the unit 4, that is application of Fourier representation and properties of Fourier transforms. So we mainly focus on sampling, a few problems on it, aliasing effect, and reconstruction of the signal, ideal case as well as practical case. It hardly takes me another 25 to 30 minutes in order to conclude this chapter. Let me share my screen. In lecture 37, the topics covered are sampling, aliasing, and reconstruction, and few examples on it. And we will give some concluding remarks on this chapter number 4. I just want to summarize or start from the place where we had left in the previous session. We just started to understand what is the meaning of reconstruction of continuous time signals for samples, from samples. If x of n is the input, the reconstruction system should generate x of t at the output. The x of t is a reconstructed signal. Originally, we had x of t. I had repeatedly quoted you an example of me speaking at this end and you people are hearing at the other end. Whatever I am speaking in real time, if we call it as x of t, whatever you are hearing, it is a reconstructed signal x of t. And in between, whatever the signal transformations are happening during this process of transmission, it is x of n, capital X of j omega, whatever the Fourier representations we have. Okay, so we go in detail about this reconstructions of the system. We had taken the same example or same concept in the previous class. Just to summarize or recap or recalling, I took it once again. If this thick line, solid line is, which we represented as x2 of t, is the original signal, and we have taken a samples with a vertical bar, and once we reconstructed it, the dashed line will show the reconstructed signal. Of course, it is not accurate, but it will resemble as if it is a original one. Okay, so this is how we need to find out the signals after the reconstructions. To repeat again, the smoothness of the time domain signal, it changes with respect to the sampling rate, or else I can say maximum frequency that is present. Okay, so hence constraining smoothness in the time domain corresponds to limiting the bandwidth of the signal. Bandwidth is nothing but frequency bandwidth. Okay, so I had quoted these statements in the previous class. So I have taken it once again because it is a very important one, a very important concept. I even quoted you an example of recording temperature at every 1 hour in a day, so that we can plot a graph which accurately, somewhat near to accuracy, it will depict the temperature variations on the day that we have recorded. If at every 5 hours if it was recorded, it will not be as accurate as the sampling taken at every 1 hour. And if you take it at every 1 minute, it will be much more accurate. So keeping this in mind, we took some real time, some signal, some continuous time domain signal, and we recorded which is a maximum frequency. Maximum frequency is the abrupt variation that is causing sudden variation. There the maximum frequency component exists. We note it as Fm, F suffix m, or angular frequency omega m. We call it as maximum frequency. Okay, and you are sampling. How much samples? How to sample this signal? If that question arises, the scientist called Nyquist have given his the criteria, calling Nyquist criteria or Nyquist rate. It says that the sampling frequency should be at least, or it should be greater than 2 times of the maximum frequency that is existing in the continuous time domain signal of our interest. With this selection, with this criteria, we end up extracting all the possible samples which are needed, which are sufficient in order to reconstruct the signal which looks resembles reasonable at the output of the reconstruction system. So hence omega s we call it as a sampling frequency, omega m we call it as maximum frequency that is existing into it, and minimum sampling frequency that you should select is omega s is equal to 2 omega m. This is a minimum sampling frequency we need to select. Okay, and if you substitute omega is equal to 2 pi f, you get it as 2 pi cancels, fs greater than 2 fm. That is also okay. If you substitute fs with 1 by ts, you will get it as, in terms of ts, you can record it. So ts is less than 1 by 2 times of fm. So you can depict it in any manner. Okay, so if x of t is the signal, continuous time signal, to extract its samples, we denote it as x of nts, where n is an integer, ts is a sampling period. Okay, so these all concepts we'll use in order to understand the further things. To make our understanding more accurate, I have taken an example here. In this example, I'll be providing you with a time domain signal, and you need to select the sampling interval. If this is a time domain signal, what is the sampling interval or sampling rate I need to choose? That is omega s or ts or fs that we need to choose in order to accurately represent the sequence. Determine the condition on sampling interval ts so that x of t is uniquely represented by the discrete time sequence x of n equal to x of n ts. So what is that ts we need to, what is that sampling period we need to use in order to fetch the samples for the signal following the Nyquist criteria? That is what we will study now. In order to apply a sampling theorem, we must first determine the maximum frequency omega m present in the x of t. What's the maximum frequency present in the x of t? That we should first fetch. This is x of t. X of t is given as sine 10 pi t divided by pi t. Okay, so the ft pair is capital X of j omega. It's a rectangular pulse, omega less than or equal to 10 pi. So this is omega s. Here also you can fetch, or here also you can fetch. So omega s, omega m. It's omega m, maximum frequency. Maximum frequency omega m is 10 pi. This has occupied a place of omega. So that's the only frequency component that is there here. So omega m is equal to 10 pi is a maximum frequency. Hence, we need to apply the formula. So let me apply the formula. If this looks complicated for you, the sampling or Nyquist rate says that omega s should be minimum 2 times of omega m. So omega s should be greater than 2 times of 10 pi. Omega s is equal to greater than 20 pi. So what is omega s? You know that omega s can also be represented as 2 pi fs, or else it can also be represented as 2 pi by ts, because fs is 1 by ts. So I have been asked to find out ts. Hence I relate this omega s. I replace it with, see, omega s is equal to 2 pi. I replace it with 2 pi by ts is greater than 20 pi, or it can also be written as pi and pi cancels, 2 and 2 cancels, 20 cancels. So 1 by ts greater than 10 you get. So take its reciprocal. When you take its reciprocal, the relational symbol, the conditional symbol inverts. So when you reciprocate it, this becomes less than from greater than. So ts is greater than 1 by 10. So this is your answer. If you take the sampling period less than 1 by 10, then you will be able to accurately or uniquely represent this x of t by the discrete time sequence x of n is equal to x n ts. That's the meaning. So uniquely represent means you don't miss out. The error introduced will be very less by taking that sample. Okay, so that's the meaning. We shall have few more examples. So this is x of j omega representation. So 10 omega 10 pi minus 10 pi. So just to have your a link between this mathematical equation and graphical diagram. Now we have one more question here. Determine the condition on sampling interval Ts, same question, so that x of t is uniquely represented by the discrete time sequence x of n is equal to x of n Ts. Same thing, same question. X of t is given as this particular time domain signal. We have three terms here. Look at these terms, three terms. Which of the three terms has a maximum frequency that you need to fetch? The standard or general form of this is cos of omega naught or omega t. So in place of omega I am having pi here, in place of omega I am having 2 pi here, in place of omega I am having 4 pi here. Out of these three terms, these three frequency components, which one is the highest one? 4 pi is greater than 2 pi as well as pi. Hence, the maximum frequency in the given signal omega m is 4 pi. That's the maximum frequency. And the Nyquist rate says that for sampling theorem, Nyquist rate or sampling rate says that omega s should be greater than 2 times of omega m. That's why it should be greater than 2 times of 4 pi. So therefore, omega s should be greater than 8 pi. Now I have been asked to find out Ts. So what is the substitution for Ts? Omega s is equal to 2 pi by Ts greater than 8 pi. So pi and pi cancels, 2 ones are 2 fours are. So hence it is 1 by Ts greater than 4. I reciprocate it and invert this conditional symbol. Ts less than 1 by 4 is the answer. So that's your answer. So if your sampling period is less than 1 by 4, then you'll be able to uniquely represent x of t using x of n is equal to x of n Ts. Okay, so similarly, we will take one more example. Okay, so here we have been given the same question. The time domain signal is x of t is equal to cos 2 pi t sin pi t by pi t 3 sin 6 pi t sin 2 pi t by pi t. See, whenever you get this question, either in your competitive exams or exams, don't bother much. Just look at the question. We have been asked to find out only Ts. I don't intend to find its Fourier transform or do anything with this. I just want to calculate what's the maximum frequency component that is possible in this equation. You know that cos A and sin B, cos A sin B. Cos A sin B will result in cos A plus B. You have that A plus B one time and A minus B the other time. Similarly for sine and sine, you'll be having A plus B component and A minus B component by trigonometric formulas. So by applying trigonometric formulas, if I call this as A and if I call this as B and if I call this as P and if I call this as Q, we will be doing one time A plus B and other time A minus B, sine or cos otherwise here according to the formula. I don't go in detail there. Here also P plus Q once and P minus Q the other time. To have the maximum frequency, I need to go with only the sum operation because this can only give us the maximum out of it. 2 pi minus pi is pi, so I'll ignore it. Okay, so this is just pi, I don't want it. So here again 6 pi minus 2 pi is just 4 pi, I ignore it because addition will result in greater number. So here it is 2 pi plus pi will result in 3 pi. Let me check it. So here 6 pi plus 2 pi will result in 8 pi. So out of all these things, this one is a maximum. So therefore, omega m is equal to 8 pi. So Nyquist rate says that omega s should be greater than 2 omega m. So this is 2 8s are 16 pi. So omega s can be represented as 2 pi by ts. Pi pi cancels, 2 1s are, this is 2 8s are. So 1 by ts should be greater than 16. So if you invert this conditional thing operator and conditional symbol and say reciprocate it, you will get the answer as ts less than, sorry, here it should be 8 because 2 ones are 2 8s are, it is 8 here. So TS less than 1 by 8. This is the sampling period in order to uniquely represent x of t. Okay. We can also ask the problem in this manner. Here the signal given is in terms of the graphical representation. This is a ft of x of t for problem. So here also you can find out the maximum frequency. I had earlier said with some intention. Here I shown this graph just with some intention. Whatever you have here, that itself is a maximum frequency. Right? Itself is a maximum frequency. So the period, it can also be fetched from the ft's graph. So to fetch that from the graph, so from here it starts rising, decreasing, 0, again like sort of sudden increase and decrease. So thereafter it is not given. So from here to here, we might call it as plus omega m. From here to here we call it as minus omega m. Okay, so what's the maximum frequency by looking at the graph, which is equal to from 3 pi 4 pi. It is in between these two things. Let me write it as 4.5 pi. 4.5 pi. So hence omega m is equal to 4.5 pi. That is what is the maximum frequency in the given signal. Now Nyquist rate says that omega s should be greater than 2 into omega m. So omega m is 4.5 pi. So omega s is equal to greater than 9 pi. So here I substitute 2 pi by ts, which is greater than 9 pi. So this is equal to pi and pi cancels, 1 by ts greater than 9. So sorry, 2 is a pi, only pi get cancels. The answer is reciprocate it and invert this conditional symbol. Ts will be less than, so if I take this 2 on the other side, 9 by 2 it is, 1 by ts greater than 9 by 2, 1 by ts greater than 9 by 2. So if you invert it, you will get it as ts less than 2 by 9. So this is a sampling period for uniquely representing x of t. I hope there are no doubts. Problems are very simple. Next comes the next topic, aliasing. So what's the meaning of aliasing? That is what we need to understand. To understand the concept of aliasing, we should have the prerequisite knowledge of sampling. And aliasing effect can be observed in the frequency domain. Let us understand what is this aliasing is. As the TS increases, sampling period increases. If sampling period increases, what happens to the frequency? Frequency decreases because TS is inversely proportional to Fs, or else Ts is inversely proportional to even angular frequency, 2 pi by Ts. Omega is equal to pi by T. That's why. So if Ts increases, omega s decreases. The shifted replicas of x of j omega move closer together. So what happens if you increase Ts? I kept on telling you that you should have this much sampling period. Then only you can uniquely represent. What happens if I don't follow that? What happens if I ignore Nyquist criteria? Ignoring Nyquist criteria means doing this. Increase Ts. I just want to increase the sampling period of recording the temperature. I don't want to record at 1 hour. I want to record it by increasing the time, like 5 hours. What happens? Error introduced will be more. Same thing will be happening here. The shifted replicas in frequency domain, what happens is the shifted replicates of x of j omega move closer together. I'll show it in the graph. Finally overlapping one another when omega s falls below 2w. I'll show it what it is. So, or else I can write it as 2 omega m. So if it ignores the Nyquist criteria, then there will be overlapping. That is what is termed as aliasing. Remember one thing, the error introduced by not following sampling theory or theorem or Nyquist criteria is termed as aliasing. It causes overlapping in the replicas in the frequency domain. That is what is called as aliasing. Aliasing is a phenomenon. This is one more definition. Aliasing is a phenomenon of a high frequency continuous time component taking on the identity of the low frequency discrete component. I'll explain it with a graph. Aliasing distorts the spectrum of the sampled signal. So x of n DTFT pair is x of e raised to j omega. So which is represented using ft x delta of j omega by substituting omega is equal to capital Omega divided by ts. We already know it. So I'll take the graph here. This is accurately represented or uniquely represented, and Nyquist rate and sampling theorem followed frequency response. See, this is a frequency spectrum and these are replicates. So these replicates are well distanced. When these are well distanced, there will be no loss of information. Now you can see here, I increase TS. If I increase TS, what's the meaning? It is like I'm decreasing frequency. When I decrease a frequency omega s, so now omega s is from here to here. Now if I decrease it, it will come closer. So it is coming closer here. So it is coming closer. Now it is marginally okay. Marginally we are able to sample the signal uniquely. Now what if I still more increase sampling period and decrease the frequency, there will be a overlapping. And you can see that this is a very important frequency component for me. Here, this part of the frequency component from here, okay, from here up till here, no problem. So this part of the frequency component, comparing, taking only this one, this is a high frequency component. These are lower frequency. Omega is a very less number here. Omega equal to 0, 1, 2, 3. It is less. This is lower frequency. This is higher frequency. The higher frequency components will be merging with lower frequency component of the next replica. Hence the information gets lost or it gets distorted. That is what I have taken here. Aliasing is a phenomenon of higher frequency continuous time components taking on the identity of the lower frequency discrete components. And aliasing distorts the spectrum of the sampled signal. So what if you don't follow Nyquist criteria? Aliasing is a result of it. It means overlapping in the frequency spectrum happens. Okay, so that's why you should be very careful. So in the first diagram, omega s is selected as 3 times of w. Here omega s is selected as 2 times of w. Here omega s is selected as 1.5 times the w. See, as I decrease the frequency, aliasing is more visible, more prominent. So hence sampling is very important. So aliasing is a negative effect, okay, on the sampling. That's it. Now comes the last topic of this chapter, reconstructions. In reconstructions, we will be studying two different concepts. One is ideal reconstructions, which is normally practically not possible. Second one is practical reconstruction. So here we go on. So x of t's ft pair is given here. Ft representation of the sampled signal, we write it as capital X delta j omega is equal to 1 by ts summation x of j omega minus j k omega s. This we could write by deriving the relation between ft and dtft. Ft and dtft are related. With that equation I have written it here. Now the goal of reconstruction, what's the goal of reconstruction? Why we need to do the reconstruction? The goal of reconstruction is to apply some operation to this x delta of j omega. It's a sampled signal's Fourier representation. So we need to apply some operation to this signal. Why? Because I want to convert it back to x of j omega. Because I want to retrieve the original signal. Any such operation must eliminate the replicas. So what is that? I have shown it in the previous diagram. So if this is similar kind of diagram, we had shown it for ft also. Actually x of j omega, we had got only single spectrum, and because of the conversion to the sampled signal discrete domain, so we get the replicas like this. I want to remove this replica from here to I want to go back to this. So what happens? I want to retain only this. I want to take out all these other things. So what I have to do? I want to retain this. So I put a rectangular pulse. I multiply with this. Rest everywhere I'll keep it 0. So rectangular pulse exists only overlapping to this. So when I multiply, this will be retained. These all things will go off. That is what is a trick I use. Just here. Operation must eliminate that replicas or images of x of j omega that are centered. Okay. So I select the signal because there is a scaling 1 by ts. So I need to multiply with ts so that to nullify that effect. So this is nothing but h r j omega is a rectangular pulse omega s by 2 plus omega s by 2. So amplitude is ts. So when I multiply this with this signal, so this signal would have looked like x delta of t. I'm writing x delta of j omega would look like 1 by ts, and replicas will be like this. So when I multiply with this, what happens? Only this will be written, this will be gone, only this will be written. 1 by ts into ts will give me 1. So with that intention, I'm taking it. So I need to multiply it in order to get what? X of j omega. That's the original thing. I'm retrieving back my signal that we have already processed. Note that multiplication by hr j omega will not recover capital X of j omega from x delta of j omega if the conditions of sampling theorem is not followed or not met, and if aliasing occurs. If there is aliasing, if you have not followed sampling theorem, there is no way you can get back to the original signal or reconstructed signal. Remember that. So here I was drawing simply. Here is the diagram. So this is x of j omega. This is x delta of j omega. I want to produce this. I want to produce this from using both of these signal. So I multiply. I multiply with this ts. It is 1 by ts. It becomes 1. So I will be reproducing this one. So this is ideal reconstruction. Okay. So A is spectrum of original signal. B is spectrum of sampled signal. C is frequency response of reconstruction filter. We call it as reconstruction system. System and filter are interchangeably used. Remember that. Okay. System means also same. Filter is also same. So we are using this in order to reconstruct the signal. So multiplication in frequency domain transforms to the convolution in the time domain. That you know. If I multiply these two signal in time domain, it is convolution. So that's why. So that is what I'm writing here. This is frequency domain. This is time domain. So multiplication becomes convolution here. So HR and HR j omega are a FT pair. So what I'm doing is HR j omega is a rectangular pulse. We already know it. This is a rectangular pulse from minus omega. I just take it here. Here it is. TS omega s by 2 omega s by 2. This is HR. Okay, I just write it in this fashion. Okay, so now what I'm doing is we have some standard formulas, right? So the FT pair from this we can get it as, see, we had a standard pair. So whenever we had let me write it here, sine wt divided by pi t in the time domain, its FT pair is its FT pair result in rectangular pulse, that is x of j omega. It will be there for omega less than or equal to w, otherwise. So use this. Here I'm having this diagram. I'll draw it here. So it is 1 for minus w till plus w. That is what is the signal. For that I got it as sine wt divided by pi t. Similarly, if I ask you to write the FT pair of this signal, you just hear ts is amplitude, ts I wrote it, sine in the bracket wt. What is w? In place of w, what I'm having? Omega is by 2, omega is by t I'm writing. So t in place of t, I'm having t divided by pi t as it is. So using this pair, FT pair, I am able to write the time domain signal of whatever filter we had taken, reconstruction filter I have taken here. Okay, so that's why what I do is convolution HR of t convolved with x delta of t. What is x delta of t? X delta of t is a sampled signal of the continuous time, which can also be represented as summation of shifted impulses, shifting property of the delta function. It will fetch individual value of amplitude of x of n at given n, and when you add it you will get the sampled signal. So summation x of n I'll take outside, hr of t multiplied with delta, that is delta function, we get it as replace t with t minus nts. This operation we already know. So this is the x of t in the time domain. In frequency domain it is just x of multiplication of these two things. Okay, and even hr of t minus nts, replace t wherever you have t, replace it with t minus nts. Either you can do here, or else you can even convert it to sinc function. So these two are interchangeably used, both are same, both are same. So interchangeably you can use in place of hr of t. So only thing is, in place of t you have to substitute t minus nts. So but it is ideal reconstruction. Practically it cannot be implemented because of two reasons. The first reason is it's a non-causal system. You check here, n is varying from minus infinity to plus infinity, even sinc function varies from minus infinity to plus infinity. So hence the output x of t depends on the past and future value of the input, hence it is non-causal system. Real time systems are called as causal system. Non-causal systems are not called as non-real real time systems. So when it is not real time system, in real it is not possible. That's why practically cannot be possible because of this. The influence of each sample extends over an infinite amount of time, because hr of t has an infinite duration. So hr of t, when you convert into time domain, you get a sinc function. Sinc function extend till infinity. Small signal will be present even till infinity. Hence, so whatever signal that extends till infinity, practically it is not possible. That's why ideal reconstruction is not possible. There will be some errors. So whatever I speak, the same thing will not listen. There will be some changes in my voice modulation, some changes in my pitch frequency or something at your end when you listen. Okay. So this is how it looks. Sampled signal hr of t in time domain when you convolve it. So it is like taking the signal everywhere. This is how the reconstruction is, ideal reconstruction is, which is not practically possible. Now practical reconstruction, we'll look into it before we conclude this session. So it's very simple to understand. Just here, we use a zero order hold reconstruction technique. It holds the x of n for ts seconds. What it does very simple work. At 0 it comes, it is having some value. So when you up till it takes the next value at next integer, that is equal to 1, it will hold its value, like it will hold its value like this. See here, it is holding its value. Now next value, when it comes, it will release the hold. Next value it is raised. Again it will hold for until we arrive at the next n equal to 2. So it is holding. Now it will drop. So hold and release, hold and release. This is called zero order hold. When you hold it like this, rather than getting a signal in this fashion, actually you would have got like this, right? You get somewhat in this fashion, some plain some glitches, small, you know, stop and hold, it looks like this. But it is, when the sampling time is too less, this can be ignored. The voice or the signal looks very much reasonable. So hence this is preferred. This is a practical reconstruction of zero hold. Now how to do it? So what we do is, wherever I have a sample, I multiply it with this one. I convolve it with h naught h0 of t, h naught of t. So what it is, this signal is from 0 to ts, it maintains a rectangular pulse. Actually till now we have studied signals like this. We had a signal like this. Here we had a minus t naught, we had t naught here. Okay, so such signals we had taken. Now what we need to do is, we need to get this. How to get this? Okay, so to get this, what we do is, I scale it. So for example, if I call it as ts, this whole thing was 2 ts. I want to compress it. To compress it, what I have to do? So I have to scale it by 2 times. So this becomes minus ts by 2. This becomes ts by 2. Okay, ts, it is time scaled. Now let me call it as x of t. Now I want to get this one from the signal. How to get it? Shift the signal by 1 time onto the right, by not 1 time, by ts by 2 times. Shift this by ts by 2 times. Okay, so what I do is, I shift this by ts by 2 times, so I get it as 0 to ts. You just remember this because in the next slide I'll be using this concept. Yeah, here. So x naught of t is equal to the in reconstruction from zero order hold h naught of t convolved with the sample signal. This is nothing but x delta of t. The sample signal can be represented as this summation x of n. This total I can write it in this fashion. It is written there. In frequency domain, it is just a multiplication. Now h naught of t was like this, if I'm not wrong. Yeah, it is right. It is ts. Here it is 1. So how to represent this in frequency domain? For that, I just want to show you some standard definition. The standard definition says that, you know, so it goes like this. So when you have a signal like this, minus t naught to plus t naught, and it is 1, you have the ft pair as 2 into sine omega t naught. I'm just taking from the previous chapter. Okay. So 2 by omega sine omega t naught. So that is what you need to write. So here the signal is here. It is half. In place of t naught, if I want to write ts, but it is, it is somewhat the signal taken from the shifted version. You know, it was taken from the shifted version like this. It is taken from this signal, shifted version of this signal. So that's why we represent this signal ft pair as sine 2. I'll write it first. 2 sine omega. In place of omega, I write it as omega. In place of t naught, what I have to write? In place of t naught, I'm having ts by 2 divided by omega. So this is there, this component is there. Why this e raised to minus j omega ts by 2 component exists? This exists because it has been shifted. When it is shifted by right onto right in the time domain, then it will introduce a complex sinusoid in the frequency domain, minus j omega. What's the amount of time it is shifted? It is shifted to the right, ts by 2. ts by 2. ts by 2 amount of time it is shifted. That's why this component added. So this and this you can match it now. It is same. Okay. So hence I just read it. A linear phase shift corresponding to a delay of ts by 2 seconds. That is what you have seen now. The distortion of the portion x delta of j omega between minus maximum frequency. The distortion is produced because of curvature in the main lobe. This is because reconstruction practically it is not accurate. Some part of distortion will be existing. The distorted and attenuated versions of images of x of j omega centered at non-zero multiples of omega s is shown in the next slide. So this is after sample signal. If you write the spectrum, replicas will be there. Now I use zero order hold signal. So this in frequency domain, in time domain signal, it looks just h naught would look like simple, this one. So in frequency domain, it is looking like this, main lobe. But still, there will be small component exist here. So hence, this is phase. You right now ignore phase. When I multiply these two things, I would get in this fashion. I did not wanted these things, but still I get it because it is practical, distorted, slightly distorted. And you can see that this and this are not exact, but it is somewhat reasonable. You can connect that. Okay, this signal is somewhat looking in this fashion. So that is what happens in the reconstruction. So with this, we are concluding this chapter. Thank you.